Okay, let's unpack this. Today, we're jumping into a deep dive on a challenge that's becoming, well, really important as we push the boundaries of large language models, LLMs, using reinforcement learning.
Right.
Think about tasks where you need verifiable answers, like complex math problems or, writing functional code. RL is pretty key for training LLMs on these, going beyond just the initial pre-training phase.
Exactly. It's about fine-tuning them for specific skills.
So our source for today is this fascinating paper just out on RLinux. It's called The Entropy Mechanism of Reinforcement Learning for Reasoning Language Models.
hmm
And this paper really zeroes in on a major obstacle, a real hurdle when you try to scale up RL training for these big models.
Yeah, something that consistently ran into.
So our mission for this deep dive
Yeah.
to really understand the obstacle, the paper calls the collapse of policy entropy,
hmm
figure out why it happens, and crucially, what this research suggests we can maybe do about it.
And what's really surprising, I think, is how the paper uncovers this very predictable pattern. Right there in the middle of what you'd think is just chaotic training dynamics, they found this clear relationship linking the entropy problem directly to how well the model actually performs.
Okay, so let's set the scene a bit. We're using RL, reinforcement learning, to train these LLMs on specific tasks where you can check the answer, right? Verifiable tasks.
Right. Like math or code generation.
The goal seems straightforward. Maximize the reward signals we get back from some system, a verifier, that checks if the model's output is correct. The paper mentions using standard methods for this, policy gradient methods like GRPO, reinforce plus array, things like that.
Mhm.
They reference some equations about how the model updates its probabilities based on those rewards.
Exactly. And the core concept we really need to get our heads around here is policy entropy.
Okay.
In simple terms, it's basically a measure of how uncertain or, random the model's decisions are when it's generating text, like picking the next token.
So high entropy means it's considering lots of options.
Yeah, exactly. High entropy means it's looking at a wide range of possibilities, maybe with similar probabilities. Low entropy means it's very, very certain about the next step. It assigns a really high probability to just one or maybe a few options.
Oh, okay.
And this is fundamentally tied to the exploration-exploitation trade-off in RL. Entropy kind of quantifies the model's willingness to explore less obvious paths to try something different.
Right. And what did this paper find? You said it was consistent. What do they see across all their experiments?
This is where it gets really striking. They observed what they call a consistent pattern, and this was across 4 different model families, 11 specific models, various tasks, even 4 different RL algorithms.
Right. Okay. So pretty broad.
Very broad. And the pattern was policy entropy sharply declines to near zero in a few training steps. Basically, the model's decision-making becomes incredibly rigid, incredibly certain, really, really quickly.
Whoa, so it just locks in super fast. It loses that randomness, that potential for exploration almost instantly. What's the consequence of that happening so fast?
Well, the consequence is a pretty predictable performance plateau.
Plateau. Okay.
When the model stops exploring because its policy entropy is practically zero, its validation performance just stops improving significantly. The paper highlights this key finding, I think is from their figure 2. Over 93% of the performance gains they observed actually happened in just the first third of the training steps.
93% in the first third.
Yeah, and this correlates almost perfectly with the period where most of that entropy loss happens. So after that initial burst, you've got 2/3 of the training time yielding only tiny marginal returns unless you actively do something to counteract this entropy collapse.
Okay, wait, that's huge. So potentially 2/3 of the compute, the training effort, is essentially wasted because the model just becomes too rigid too early.
That seems to be the implication, yeah.
But you mentioned predictability. How predictable are we talking here? It sounds messy.
This is maybe the paper's most fascinating empirical discovery. They found this really striking, simple exponential relationship between the validation performance, let's call it R, and the policy entropy, H. The formula is just R equals minus A times the exponential of H plus B. R equals AXPH plus B.
Huh. An exponential relationship.
Exactly. It's shown really clearly in their figure 1. And astonishingly, they show in figures 3 and 4 that this simple formula fits the experimental data incredibly well across all those different models and tasks they tested.
So it holds up across the board.
It really seems to. It's almost like a universal curve describing the specific limitation in RL training for these models.
The universal curve.
Yeah.
That feels, counterintuitive for something as complex as training these huge language models. So if this formula really holds, what are the big implications? What does that tell us?
Well, there are two main things, I think. First, predictability. Because this relationship is so consistent, you can actually predict how well the model will perform later in training based on measurements taken really early on.
Really? How
And
really?
Figure 5 in the paper shows they could predict the final performance using data from just the first 15% of the training steps, and the error rate was remarkably low. The average prediction error was between like 0.5% and 1.9%.
Wow. So you could potentially know if your RL fine-tuning is likely to succeed or plateau very early in the process. Save a lot of compute, maybe?
Potentially, yes. That's a big implication. The second one is about the performance ceiling. Look at the formula again. R equals SPH plus B.
Okay.
If policy entropy H goes all the way down to 0, which is what they observed happens quickly, then H is 0, XPH is 1, and the maximum performance you can reach is just R equals A plus B.
Ah, I see. The B minus A value.
Right. This suggests there's a kind of deterministic upper bound on the performance you can achieve if you let that entropy collapse happen. It strongly implies that standard RL methods, just left to their own devices, might not be able to push the model's performance much beyond its pre-trained capabilities, precisely because of this entropy bottleneck. It gets stuck.
That makes a lot of sense, actually. If it stops exploring, it can only optimize the limited set of strategies it converged on so quickly. And those coefficients in the formula, A and B, A seems like the rate it trades entropy for performance, and A plus B is that performance ceiling. Did the paper find anything interesting about them?
Yes, they did. Even those coefficients show some predictability. They found they seem to be algorithm irrelevant, meaning the same A and B values work pretty well regardless of which specific RL algorithm they use, GRPO, reinforce, plus plus besh, etc. That's figure 6.
Interesting.
And maybe even more interesting, they found that A and B vary smoothly in a log linear way with the model size. Figure 7 shows this.
Log linear with model size.
Yeah,
Yeah.
which hints that you might even be able to predict these parameters for, say, a much larger model based on experiments you run on smaller ones. It adds another layer to this whole predictability story.
Okay, so we've got the problem identified. Policy entropy collapses super fast. It causes performance to plateau. And there's this surprisingly predictable mathematical relationship describing this limit. The big question now is why? Why does this collapse happen? The paper dug into the dynamics, didn't it?
Exactly. If it's such a predictable bottleneck, we need to understand the mechanism driving it. And yeah, the paper provides a theoretical analysis of how policy entropy changes during training, specifically for softmax policies, which is what LLMs use to choose the next token.
Right. So what's the key finding from that analysis?
The key finding mathematically is that the change in policy entropy from one training step to the next is approximately related to the negative covariance between two things: the log probability of an action the model takes, and the change in that action's logit.
Okay, logic. That's like the raw score before the softmax function turns it into a probability.
Exactly. Think of it as the pre-probability score.
Okay, let's try and simplify that covariance idea a bit. The paper connects the change in the logit to something called advantage under these RL algorithms, right?
Yes, that's a crucial link. Under common methods like policy gradient, the change in an action's logit is basically proportional to its advantage. And advantage is simply how much better or worse taking that specific action was compared to the average expected outcome from that state.
So putting it together.
Yeah.
The change in entropy is related to the covariance between how likely an action was and how good or bad it turned out to be compared to other options.
That's a great way to put it, yeah. The intuition is sort of like this. If an action was highly probable, the model was already confident about it, and it turned out to have a high advantage, which is a really good move, that's a positive correlation or positive covariance.
Right.
The model sees its confident choice was rewarded, so it becomes even more certain about that action in the future. And that increased certainty directly decreases the overall policy entropy.
Okay, makes sense.
But conversely, if a rare action, something the model wasn't likely to do, surprisingly has a very high advantage. Maybe it found a clever shortcut that's a negative correlation or covariance. The model is surprised by the success of this low probability action, and that surprise signal could actually increase entropy, making it less certain and potentially encouraging exploration around that surprising success.
And did they check this theory against the actual training data? Did the covariance match the entropy changes?
Absolutely. Figure 8, the left panel, provides really strong evidence. They plotted the actual observed changes in policy entropy during training alongside the dynamics of this calculated covariance term. And the two curves track each other very closely.
Ah, Okay, so the theory holds up.
It seems to, yeah. And crucially, they find that this covariance term remains mostly positive throughout training.
Mostly pot.
Yeah, which means the dominant effect is that first scenario. High probability actions getting reinforced because they also have high advantage. This consistently positive covariance reinforces actions the model is already leaning towards, which, as the paper says, further explains why policy entropy would decrease monotonically and eventually collapse towards zero.
Okay, that connection is really clear now. The model gets rewarded for things it's already confident about, and that positive feedback loop just makes it double down, becoming more and more certain, killing off exploration. What about different types of examples? Does it vary?
That's interesting too. Figure 8, the right panel this time, shows that the covariance values actually differ based on how difficult the training examples are.
Oh, how so?
For easier prompts, where the model is likely more confident and its high probability actions are often correct and thus get high rewards, leading to high advantage, they see higher positive covariance.
Right, so the reinforcing loop is stronger on easy stuff?
Exactly. The policy confidently reinforces those already likely good actions. But for harder prompts, they see lower covariance. This suggests there's less certainty about which actions truly have high advantages. Maybe the model is struggling, its probabilities are flatter, or the rewards are less clear-cut. The feedback loop reinforcing certainty isn't as strong on those harder cases.
Fascinating. So the analysis really points the finger squarely at high positive covariance as the main driver, the culprit, for this rapid entropy collapse,
Yeah.
which logically suggests a strategy, right, if high covariance is the problem.
Then maybe you should control the updates specifically related to those actions or tokens that exhibit really high covariance.
Exactly. But didn't you say standard entropy methods don't work well?
Great. The paper addresses that first. They look at why traditional methods like just adding a general entropy bonus to the loss function or maybe adding a KL penalty to keep the policy close to the initial model often fail for these large language models.
Why is that?
Well, Section 4.1 and figures 9 and 10 show they can be really finicky, very sensitive to hyperparameters. Sometimes they barely slow the collapse, other times they can even hurt overall performance. They don't seem to reliably prevent the performance plateau. It's like using a sledgehammer when you need a scalpel.
Okay, so instead of a blanket approach, the paper's core idea is much more targeted.
Precisely. It's about restricting the update of tokens with high covariances. And a key insight comes from their Table 1, which shows that it's actually just a small portion of tokens, really tiny fraction, that exhibit extremely high covariance.
Just a few outliers.
Yeah, suggesting these outliers are dominant in causing the collapse. You don't need to regulate everything, just these few sort of overexcited tokens that are driving the certainty up too quickly.
That makes sense. So how do they propose targeting them?
Based on this, they propose two surprisingly simple yet apparently effective techniques: Klipkov and Kayalkov.
Okay, Klipkov.
For Klipkov, you identify an incredibly tiny fraction of tokens. In a sequence, we're talking like 10 euro to 10 euro, so maybe 1 in 10,000 or 1 in 1,000 tokens that have very high positive covariance above some threshold they set, like 1 or 5.
A tiny fraction.
Tiny. And for these specific tokens, you simply detach their gradients during the policy update step. You basically tell the optimizer, ignore the update signal coming from these specific tokens for this step. You stop them from pulling the policy distribution too strongly towards extreme certainty based on that single high covariance event.
Okay, just snip the connection for those few tokens
Yeah.
and Kayalkov.
Kayalkov is similar in spirit, but uses a penalty instead of a hard clip.
Yeah.
You again identify the tokens with the absolute highest covariance values, maybe the top 0.02% to 0.2%, so again, a very small set. And then you apply a Kullback-Leibler, KL divergence penalty, but only to the policy distribution over these specific high covariance tokens.
Only on those tokens.
Yes. The KL penalty encourages the model's probability distribution for just those tokens to stay closer to what it was in the previous step. It penalizes large updates driven by high covariance, essentially forcing them to retain a bit more uncertainty or explore alternatives slightly longer.
So both methods are really focused on just dialing back the influence of those few tokens with extreme positive covariance.
Yeah.
Did these targeted methods actually work? What did the experiments show?
Well, the results presented in Table 2 look quite positive, yeah. They found that these covariance-aware methods achieved, quote, non-trivial improvements on standard math reasoning benchmarks. And this was compared against strong baselines like the standard GRPO algorithm across different model sizes.
Non-trivial improvements, like how much?
Looking at the numbers, Klipkov and Kayalkov averaged about 2.0% higher performance than the baseline GRPO on the 7 billion parameter models they tested.
Okay, 2% is nice.
But the gains were actually more significant on the larger models. They saw a 6.4% average improvement on the 32 billion parameter model.
Oh, wow. Over 6% on the bigger model.
Yeah. And on some of the really challenging benchmarks, like parts of the IM math competition dataset, for the 32B model, the gains were over 15%.
15%. That's substantial.
It really is. And this is important because it suggests these methods are particularly crucial for enabling larger models, which presumably have more latent potential from pre-training to actually leverage that potential during RL fine-tuning. By keeping exploration alive longer, they can continue to improve. You can see this in Figure 11.
Right, Figure 11. Let's look at that. It seems to show how they work, right, on the left.
Exactly. The left panel shows the policy entropy curves. You see the baseline GRPO just collapses to near zero very quickly, as we discussed.
Yeah.
But Klipkov and Kayalkov clearly uplift policy entropy from collapse. They maintain significantly higher entropy throughout the training process.
So they successfully keep exploration going.
They do. And this sustained exploration isn't just some abstract metric. Figure 11, the middle panel, shows it correlates with the model generating longer responses, which is often necessary for complex, multi-step reasoning problems.
Makes sense. You need more steps, more thinking.
Right. And critically, Figure 11, the right panel, shows the sustained exploration translates directly into better performance over time. The Klipkov and Kayalkov curves keep climbing, avoiding those performance plateaus that plague the baseline method.
That's a really clear demonstration. Sustained entropy leads to sustained improvement.
Precisely. The paper also notes that you can actually tune the level of entropy control by adjusting the hyperparameters, like how many tokens you clip in Klipkov or the strength of the KL penalty in Kayalkov. That's shown in Figure 12. They mentioned Kayalkov seemed to provide maybe slightly stabler entropy curves in their tests.
Okay, this has been a fantastic deep dive into this paper. We started by identifying this really crucial problem, the policy entropy collapse in RL for LLMs, and saw how surprisingly predictable it is and how it limits performance.
Yeah, that R XPH plus B formula was striking.
Totally. Then we really dug into the why, understanding this covariance mechanism, how reinforcing high probability, high advantage actions drives the collapse.
Right, the positive covariance feedback loop.
And finally, we looked at these elegant targeted solutions, Klipkov and Kayalkov, that just focus on those few high covariance tokens to successfully maintain exploration and ultimately boost performance, especially on larger models.
And stepping back, the broader picture here feels pretty significant, doesn't it? RL is often talked about as like the next scaling axis for improving LLMs beyond just making pre-training sets bigger, especially for complex reasoning or tool use.
Yeah, moving beyond just text prediction.
Exactly. And this work provides a really principled understanding of a fundamental barrier to making that scaling effective. Addressing this entropy collapse seems, as they put it, pivotal to keep exploration and continuously improve. It's about making sure the massive compute resources we pour into RL fine-tuning aren't largely wasted hitting that premature plateau.
Right. Getting more bang for your buck, essentially.
You could say that. So to kind of conclude, the paper gives strong empirical evidence that there's this inherent trade-off. Performance gains often come at the cost of exploration capacity, setting a predictable limit if entropy is allowed to just collapse. Their analysis reveals the mechanism behind it, that covariance dynamic and their targeted methods successfully counteract this collapse, promoting longer exploration and leading to demonstrably better results.
So the main takeaway for you, our listener, seems to be that making RL truly effective for advanced LLM capabilities isn't just about chasing the highest reward signal blindly. It's critically about understanding and managing these internal dynamics, like policy entropy. Controlling how the model learns and becomes certain seems absolutely key to unlocking its full reasoning potential.
And maybe here's a final thought to leave you with. Isn't it fascinating that intervening with such an incredibly tiny fraction of tokens, like 0.01%, maybe even less, can fundamentally alter the entire learning trajectory? It prevents the performance plateau, changes the whole shape of the entropy curve.
Yeah, that is pretty wild.
What does it really mean that the learning process is so sensitive to this tiny set of high covariance decisions or tokens? Does it tell us something deeper about how these models learn or generalize, maybe about pivotal moments in reasoning? And now that we have this kind of fine-grained control, this specific lever targeting covariance, how do we figure out the optimal balance? Not zero entropy, because that kills exploration, but maybe not too much entropy either, because that could just be noise. Finding that sweet spot, that seems like a really interesting next step, something to ponder.
Definitely something to think about. Thank you for joining us on this deep dive.